Good morning. Today we're going to talk about section 4.1, maxima and minima. And this is really a question of what do derivatives tell us and how can we use derivatives to glean information about a function or a certain problem that we're working on. So let's start with some quick definitions. Let f, a function, be defined on a set D or an interval containing a point C. If f evaluated at C is greater than or equal to f evaluated at x for all values of x in our set D, then f of C is an absolute maximum value of f on D. And so I've drawn a little picture, and it's just a little upside down parabola, but we have a maximum occurring at C in our interval. So our interval of interest goes from x equals 0 to x equals, I'll call this point A. And so we've got all these points, but we have also got C in it. And when we evaluate our function f of x at a point C, it is certainly greater than or equal to all of the values of f evaluated at x, where x is some value in this domain D. So if I go a little to the right or I go a little to the left and I evaluate my function, I get a value that's less than f of C. And if this happens for all values of x in our interval D, then f of C is certainly a maximum. And it's easy to see when we look at this graph that there is a maximum value and where it occurs, but when we're dealing with just a function given to us as f of x equals x squared minus 4, we maybe don't see the same thing. So if there's a maximum, there better be a minimum. Let f, our function, be defined on a set D containing a point C. If f evaluated at C is less than or equal to f evaluated at x for all values of x in our interval D, then f of C is an absolute minimum value of f on D. And again, we can see from the drawing that we've got a parabola and we've got an interval of interest, and C is within this interval. So let me switch to the pen and draw this interval. C is within this interval. And when I evaluate C, or when I evaluate my function a little to the right or a little to the left of C, I get values that are greater than what's going on at C. So I know that C is going to be a minimum value. And when I look at my graph, it's pretty clear to see that at C, we have a minimum value because it bottoms out. But when I hand you a function like 4 minus x squared, we don't necessarily know. So all of these are just telling us about the necessary conditions to guarantee that there's an absolute minimum or an absolute maximum on a given interval. And we can make this more precise. An absolute extreme value is either an absolute minimum or an absolute maximum. So if I ask you to find the extreme values of a function, I want you to find the maximum values and the minimum values. And furthermore, we've got the extreme value theorem. A function that is continuous on a closed interval has an absolute maximum and an absolute minimum value on that interval. So what does this look like in practice? Here's an example. I want you to identify the location of the absolute maximum and absolute minimum value on the interval closed bracket A, comma B, closed bracket. Does the function meet the conditions of the extreme value theorem? So let's move on to the next slide and see what we're working with. Now our function f is continuous, and you can tell this because while I draw my function, I don't pick up my pen anywhere to draw the entire function. And my interval is closed. That is, I'm including my endpoints, a and b. So the extreme value theorem guarantees an absolute maximum and an absolute minimum. And now we find these absolute maximums and these absolute minimums with inspection. So we find the value where f of x is greatest, and that's when x equals a. So that's where our absolute maximum is. And we find where our value is minimum. So where does our graph dip below every other part of our graph? And that's going to be when x equals c. So let's try again with a different example. Identify the location of the absolute maximum and absolute minimum value on the interval a to b. Does the function meet the conditions of the extreme value theorem? So already I've given you an example where something's definitely different. First of all, when I go to draw this function, I have to pick up my pen to draw all of it. So it's certainly not continuous. And when I look at my endpoints, I see that they're open. They're not defined for x equals a and x equals c. So not only do I not have a continuous function, I have a function defined on an open interval. So the extreme value theorem can't guarantee anything. However, we still have an absolute maximum, and that's x equals b. When x equals b, we see that we reach the maximum value of our function, and everywhere else, the value of our function is less. And we have an absolute minimum. And that's going to occur near x equals a. Now, I say near because x is not defined at a. We would expect that this would be our lowest value, but we see that we get towards our minimum value as x approaches a. So we have an absolute minimum near x equals a, but not at x equals a. And the extreme value theorem can't guarantee that we have a minimum value at all. So if we have absolute maximum and minimum, what about a function that looks a little something like this? We've got a peak right around here, and then we drop down and we have a little trough, and then we peak again, and then we come back down and we have another trough or a valley, and then we go back up. So what can we say about these? Well, if I zoom in over here, certainly it looks like I've got an absolute maximum value, and it just depends on the size of my interval. If I include everything, then my absolute maximum occurs right here, and my absolute minimum occurs right here. But if I look at these, we say that they're local maxima and minima. That is, if I were just to consider the interval from A to B and look at these, I would have a minimum and a maximum. But clearly, this maximum is not as great as this maximum. And this minimum, where our graph bottoms out, is not as great as this minimum. So we call those local maxima and minima. Now let's talk about critical points. A critical point is an interior point of C, of a domain of a function f, at which f prime of c equals 0, or f prime of c does not exist at all. And this is really important. So if you take a derivative and you see, oh, when I evaluate it at this point, it doesn't exist at all, that tells us that something important is going on there, and we call that a critical point. Or if you evaluate at a point C your derivative and you get 0, we know something is going on there as well. So here I've drawn a little sketch, and I've got a corner, so I certainly have f prime of c does not exist right there because I've got a corner, or because the limits from the left don't equal the limits from the right of our derivative. But we know that something interesting is going on there. And from this graph, we can see that we've got a maximum point there. Now, this is the very important point. Critical points are candidates for local extreme values. That is, if I give you a critical point or you find a critical point, you're going to have to do some extra legwork to tell me whether it's a maximum, minimum, or absolute maximum or absolute minimum. Like right here. Here we've got the transition from concave down to concave up in our graph. So in the transition, much like we have in the tangent function, we have a brief point where the slope is 0. Our derivative is 0. And right here, we look at this and we see, well, it's certainly a critical point, but we see that over here we've got a minimum value and over here we've got a maximum value. So we know that it's just a critical point. But we could have said we know that something is going on there, and that's what that tells us. So here's how to locate extreme values on a closed interval. Assume you've got a function that's continuous on a closed interval. And continuous is important, and so is closed. Those are very important. We locate our critical points in our interval a to b, open interval a to b, and we find where f prime equals 0 or f prime does not exist. Then we evaluate f at our critical points and at the endpoints. The largest value is an absolute maximum and the smallest value is an absolute minimum. So what does this look like in an example? A stone is thrown vertically up and the position function is given as such. When does the stone reach its maximum height? So we're looking for a critical point that is also an absolute maximum. So I've given you a closed interval, 0 to 5, and I've given you a continuous function, minus 16t squared plus 64t plus 80. So that means that we can proceed. We've got a continuous function and we've got a closed interval. So our first step is locate the critical points by finding where s prime of c equals 0. So we go ahead and we take our derivative and then we set it equal to 0 and we solve for t. When we solve for t, we get that s prime of t equals 2. So we know we've got a critical point at t equals 2. So we set that aside. Our step 2 is evaluate s of t, our original function, at our endpoints and at our critical points. So our first step is to evaluate at our endpoint 0, so we plug 0 in and we get 0. We plug in t equals 2 and we get 144, and then we plug in t equals 5 for our final endpoint and we get s equals 0. This tells us, step 3, that our absolute maximum is 144 feet and it occurs at time equals 2 seconds. That's our lecture for today.